The objective of this video is to practice creating current linkage plots for motor windings. And if you'll recall, current linkage plots are this fundamental characteristic of our motor windings that we can then use to calculate our H field and our magnetic field. We calculate our H field by dividing current linkage by the air gap length, and of course we calculate our B field from our H field by multiplying the H field by mu naught. So we're going to work through a couple examples. In the first example, I want you to create a sketch for current linkage, and then I want you to think about and tell me what the value of P is. And if you recall, P is the number of pole pairs. So in this case, we're talking about the number of pole pairs of our winding. I'm going to work through the example now. You can choose to pause it and try it on your own, or you can follow my work. And in this example, you need to assume that each coil side has a current of ZQI in it, where the direction of that is indicated in the diagram on the left. I'm going to work this problem by following the rules that we outlined in the previous video. And so I'm going to first start by creating my plot and marking the location of my various current linkages. And following the rules of last time, we'll start by drawing a line left to right. And immediately, at 0 degrees, we hit conductors going into the page, which means that we must step up by ZQI. And so I'm just going to kind of arbitrarily, I'm going to draw this so that the step up to ZQI is on the x-axis. And I continue going left to right. And then at 30 degrees, I hit another step up to ZQI. And then I start to hit some conductors coming out of the page, so I start stepping down. And so we notice that the height from here to here is 2ZQI because we took 2 steps to get there. And we also notice that our positive and minimum peaks are the same width. And so clearly this waveform, it has a 0 average because we spent the same amount of time on the positive side as we do on the negative side. So we can just say that this is equal to ZQI up here, and this is a negative ZQI down here. So that was pretty easy, following those rules. In a more complicated winding, we might have had to worry a little bit more about enforcing that theta, or that our current linkage integral over 2 pi equals 0. The next question is, how many pole pairs are on here? Just take a second and think about this. Press play when you're ready to resume. In this case, there are 2 pole pairs. There's 4 poles. You can count them. We've got 1 pole here, 2nd pole, 3rd pole, and 4th pole. In some cases, it won't be as easy to see that, but in this winding, we can fairly easily see it. That was our first example. Now we'll work through another example. So in this example winding, you can see that we have a double layer winding. And you can see that by looking at the coil sides. At 0 degrees, 180 degrees, we have coil sides stacked next to each other. That's because this winding, we're actually only showing a single phase of a 3-phase winding, and this phase has got 2 conductors, 2 coil sides in those slots. We'll talk more about what that means later, but for now it just means that you have a distinct current density appearing twice there. And again, we're going to assume that each of the coils has an excitation of ZQ times I. So in this example, I'm going to work it by sketching the current linkage for each of the coils individually, and then summing the result up. And to simplify this, I'm going to label the coils as coil 1 through 4. So I'm going to draw a line connecting the side coming out of the page to the side going into the page, and then I'll put a label. So that's C1. Here's C2. So now you can see distinctly each of the coils in our motor. And if you'll recall from your notes before, we sketched the fundamental building block, it's the current linkage of a single coil, as I'm drawing here, where we had a single coil with a span of gamma radians located at alpha 1 and alpha 2. And we had calculated the current linkage and sketched what it looked like as follows. Alright, with that reminder, let's get to work. let's sketch the current linkage of each of these coils. For our first coil, gamma is actually equal to 330 degrees. It starts at the conductor going into the page, and then it wraps around 330 degrees this way over here. And to speed things up, I'm going to define a quantity of theta c equal to zqi by 2, so that we can just say that in this case, the current linkage on the top line is equal to 1/6 of theta c. And the current linkage of our bottom line is going to be gamma by pi zqi by 2, so it's going to end up being 11/6, negative 11/6 theta c. And going down to our next coil, for this coil, we have the opposite. Now, gamma is equal to 30 degrees, and beta is equal to 330 degrees. And moving downwards, we'll sketch coil 3. And again, we're sketching this coil right here, from 150 degrees to 180 degrees. And finally, we'll sketch coil 4. So we now have the current linkage of each coil sketched, and in order to find our total current linkage of the entire winding, we have to sum these up. We'll start by indicating where the coils are. And if we go down this line, starting from the top and moving down, we can sum each component. And so this first region here, we can say that we have 1/6 theta c plus 11/6 plus a negative 1/6 and minus a negative. And in the next quadrant, we're now going to have 1/6 minus 1/6 minus 1/6 plus 1/6, which is going to be 0. And so again, to calculate that, I summed up this value, this value, this value, and this value to calculate the total current linkage in this region to be 0. And then in this region over here, we have to do the same thing. We have to sum up our current linkage. And if you do this, you'll find the following pattern. And so we finally have our current linkage plot. This was a lot more work than following the graphical rules in the previous example, and is perhaps a great example of why you want to follow those graphical rules. However, I think that this was worth doing. It gives you a lot of insight into where this is coming from. It truly is a superposition of all of the coils in your winding to create the final current linkage of your complete winding. So the next question for you is, well, what is P? And looking at this winding, it's hard to tell. I might guess that P equals 1, as in 2 poles, or maybe I would say, well, I've got a north pole here. I could imagine that this is kind of like a south pole, another north pole, south pole, north pole, south pole, or something, and I would say, well, there's 6 poles. In fact, it's virtually impossible to tell from this winding, so we'll say not clear. However, I will tell you that this is actually a single phase of a 3-phase winding that's used in a 10-pole motor. But you could not tell that by looking at this, or at least not from your training so far. And the point I want to drive home by asking about how many pole pairs is that sometimes you can tell how many pole pairs a winding is by looking at it. This one was very obvious. Sometimes you can't tell. And the reason you can't tell with this winding is because it's called a fractional slot concentrated winding, and it has a lot of harmonic content. Remember how we talked about being able to decompose the current linkage into a Fourier series? Well, if you did that and you looked at the harmonic of each of the components, you would start to see that you have a strong component at the p equals 5 index. And we'll talk more about all of this later in the course, but this is to set the stage in a way. So finally, in summary, in this lecture, we've practiced sketching current linkage waveforms. We've practiced using this new tool that we have in our toolbox, and we'll be building on in the future. We've worked on 2 examples. One where we took used the graphical rules to sketch the current linkage, and that was a fairly quick example. and second where we actually found the current linkage of each individual coil and then summed it up to get the total current linkage of the winding. And this took quite a bit more time.